Alright, welcome back students. So today we're going to be doing geometric sequences and series and counting principles. So that's going to be the last lesson for the College Mathematics for Business and Social Sciences. So in the previous lesson we introduced the, in general, arithmetic sequences and series in general, partial sums. Today we're going to be continuing that topic and we're going to start off with the geometric series. So geometric series and sequences are one of the most commonly used and most famous sequences. So a sequence is geometric when the ratios of consecutive terms are the same. So the sequence A1, A2, A3, A4 is geometric when there is a number R such that A2 divided by A1 and A3 divided by A2, etc. is equal to R, and R is non-zero. The number R is the common ratio of the geometric sequence. Okay, so for example, sequences, right? So example 1. So we will have 2, 4, 8, 16. So it's going to be 2 to the power of n, So 4 over 2 is equal to 8 over 4 is equal to 16, 8, which is equal to 2. So in this case, our r is equal to 2, right? Okay, how about this example? So we might have negative 1/3, 1/9, negative 1/27, 1 over 8, 1, comma. So it's negative 1/3 to the power of n. So negative 1/3. So actually negative. So 1/9 over negative 1/3 is equal to negative 1 over 27 over 1/9 is equal to 1/81 over negative 1/27. So and that's actually going to be equal to negative 1/3. Okay, so and that's going to be our r. Right, r is equal to negative 1/3. Okay, so those are the geometric sequences. So the nth term, right, of geometric sequence has the following form. So the nth term of geometric sequence is a sub n is equal to a1 times r to the power of n minus 1, where r is the common ratio of consecutive terms of the sequence. So every geometric sequence can be written in the form below. Okay, so this is the form that we're going to be using it. Okay, so now let's go ahead and talk about a partial sum of the geometric sequence. So a sum of the finite geometric sequence is going to be as following. So the sum of finite geometric sequence is a sub 1, so this is the sequence, with the common ratio not equal to 1 and not equal to 0, of course, is given by the following, right? This is the formula. So if we have a finite number of elements, okay? So an example would be, let's go ahead and do 3. So if we have a sum from I equal to 1 to 12 of 4 times 0.3 to the power of I minus 1. Okay, so essentially, we know that it's going to be 4 times 0.3 to the power of 0 plus 4 times 0.3 to the power of 1 plus plus 4 times 0.3 to the power of 11. Right, essentially that's what we can have. Right, so our a1 is equal to 4, r is equal to 0.3, and n is equal to 12. So we can go ahead and use that formula. So s sub n is going to be equal to a1 times 1 minus r to the n over 1 minus r. So that's equal to 4 times 1 minus 0.3 to the power of 12 over 1 minus 0.3. So if we plug that in into calculator, we'll get that that's equal to 5.714 approximately. Okay. Here, right, you can go ahead and try this problem on your own. So if you have a sum from I equal to 1 to 10 of 2 times 0.25 to the power of I minus 1. So trying to do it on your own, trying to use the same methodics, and you will get the answer. So, okay. Now, well, what about if we have an infinite series, right? So now let's say, well, n is infinitely big. We want to go further and further. So, okay. So if we have an infinitely big series, then if r is less than 1, right? So r, absolute value of r, meaning that r is between negative 1 and 1 is not included, then the infinite geometric series, which is this, has the following sum. Right, so that sum is equal to a sub 1 over 1 minus r. Okay, So now we are able to find the actual sum. So for example, example 4. So if we have a sum from n equal to 0 to infinity, okay, to infinity of 4 times 0.6 to the power of n. Okay, so we want to go ahead and find the solution here. So we will have that by the formula, right? We have that a sub 1 is equal to 4, r is equal to 0.6. Okay, so that means that our sum here is going to be 4 over 1 minus 6, which is equal to 10. So all of those numbers for infinite long time will adapt to 10. Okay, and then last time we took a look at one of the examples. So example 5, if we have a sequence or series like this, 3 plus 0, 3 plus 0, 3 plus 0, 3 plus to infinity, right? Remember what it was. That actually was a sum, right? So from n equal to 0 to infinity of 3 times 1 over 3. Oh, no. 1 over 10 to the power of n. Okay, so then by our formula right here, our a1 here is equal to 3, our r is equal to 1/10, or it's the same thing as 0.1. So we're going to have 3 divided by 1 minus 0.1, which will be equal to 10 divided by 3, which is equal to 3.33 repeating. All right, perfect. So some of the applications that we might have. Let's take a look at one problem here. Once again, it's going to be something about investment. So, so an investor deposits $50 on the first day of each month in the account that pays 3% interest. Okay, so 3% interest, which is compounded monthly. What is the balance at the end of 2 years? Okay, so to find the balance in the account, right, so essentially 2 years. 2 years is equal to 24 months, right? We're doing the payment monthly. Okay, so we're going to have 24 payments. So that means A24 is going to be equal to, so we start with 50, and then 1 plus 0.03, 12 to the power of 24, right? Our yearly interest is essentially 3%, so we split up in 12 months, and then we put it to the power of 24. Okay, so now if we will simplify it, it's going to be 50 times 1.0025 to the power of 24, right? The second deposit, right, A23 is going to be 50, 1 plus, so that's the second deposit getting the interest, so to the power of 23, going to be 50 times 1.0025 to the power of 23, right, etc. So we're going to say, okay, well, the sum of all 24 is going to be 50 times 1.0025 times, right, because we need a sub 1, and a sub 1 is going to be this. So times 1 minus 1.0025 to the power of 24 over 1 minus 1.0025. Okay, so, right, a sub 1 is this. Okay, and that is going to be equal to $1,258.23. All right, perfect. So that essentially sums up of what we are doing with sequences and series. So now let's go ahead and move on to the combinatorics. So essentially some topics of combinatorics that we're going to explore today, and going to be some counting principles. Okay, so we're going to count some permutations and some combinations of this. So counting principles. Okay, so a simple example would be, so you place, imagine you place something, let's say a cube, or actually, let's say a piece of paper, right? In a box, right? Essentially, you try to draw a lottery. So in lottery, you put each piece of paper, and let's say you have 10 pieces of papers, and you write numbers 1 through 10 in the box. So you draw one piece of paper at random from that box. You do not see what you're drawing from, right? You don't see what number you're picking. So, but once you picked it, you look at the number, you record it, and then replace the paper in the box. Then you draw a second piece, and then you repeat that. So, and then you finally add two numbers, right? So how many different ways you can obtain, let's say, a sum of 15, right? So there you would have to think of how can you get it, right? Sum of 15, so you're doing from 1 to 10, right? So essentially, first number is going to be, well, we can start with 10, 9, 8, 7, 6, 5, right? And then second number, because we're trying to get 15, right, out of two numbers. So that's going to be 5, 6, 7, 8, 9. Okay? So essentially, we have 6 different times, right? 6 different ways we can pick that. So essentially now we're going to be introducing some of the formulas, right? Some of the formulas that will help us do this process much quicker if we have more elements. So one of the fundamentals of counting principles is, well, let E1 and E2 be two events. The first event, E1, can occur in M1 different ways. After E1 has occurred, E2 can occur in M2 different ways. The number of ways the two events can occur is M1 times M2. Okay? And so, of course, you can extend it to 3 or more events. So, for example, if you would have number of ways that 3 events can occur, it would be M1, M2, and M3, right? And etc. You can do that more and more as you wish. So, okay, then the first thing we're going to talk about is going to be permutation. So a permutation of n different elements is an ordering of elements such that one element is first, one is second, one is third, and so on. So essentially, order matters, right? So what order you choose for your elements is very, very important. Okay, so essentially, so what you can have is as following. So let's say you have 6 letters in the alphabet, right? 6 letters from the alphabet. So I'm going to say, well, it's going to be A, B, C, D, right? So how many permutations of the letters they're possible? So that means that order does matter, but we are able to choose. So in the first position, any of the 6 letters can go, right? So 1 out of 6. Then in the second position, any of the 5. Third position, any of the 4. Third position, any of the 2, etc. Right? So how do we, by the counting principle, right? By the counting principle, we have 6 events, essentially. So that means the total number, and I'm going to say permutation here, is going to be 6 times 5 times 4 times 3 times 2 times 1, which is equal to, remember, last lesson we learned about a factorial. So this is 6 factorial, and that's equal to 720. So that is the reason why we learned a factorial. Now we can solve problems, right, based on the permutation. So let's recall the factorial from the last lesson. So we have the number of permutations of an n element is n factorial. In other words, there are n factorial different ways of ordering n elements. So you can imagine, the more elements you have, the bigger the permutations are present, right? Try it with 10 or 20, 50. That number will be huge. So essentially, the permutation in this sense, we can have a formula, right? So a formula for the, let's say we take a look at one more, or actually, we're going to take a look at formula first, and then we're going to take a look at example for. So the number of permutations of n element taken are at the time is. So depending how many elements we need to take at a time, because sometimes we can have multiple elements, right? And so what would be an application of that problem? So let's take a look at this problem. So assume, right, we have 8 horses that are running in the race, right? In how many different ways can those horses come in first, second, and third places? Assume that there are no ties. So that means we're picking 3 elements, right? 3 elements from all of the 8 elements, right? So by permutation, right, we're going to have that e of 8 and 3 is going to be 8 factorial over n minus 8 minus 3 factorial. 8 minus 3 factorial. So that's equal to 8 factorial divided by 5 factorial. So now let's remember the definition of factorial. It's going to be essentially 8 times 7 times 6 times 5 factorial divided by 5 factorial. So 5 factorial cancels out. So we only left with 8 times 7 times 6. And that's equal to 336 ways, right? So out of 8 horses, the 3 horses that come first, second, and third, you have 336 different outcomes, right? So when you were betting on the horse during the race, the outcomes, the probability that the horse that you bet on is very, very small. Or even that the horse, one of the horses you bet on going to come in the first, second, or third place are pretty small. Okay, so now we can also have distinguishable permutations. So the definition of distinguishable permutations is, well, consider a set of n objects that has n1 of one kind of objects, n2 of second kind, and 3 of the third kind, and so on. With the total number would be the summation of them. The number of distinguishable permutations of an object is as following, right? So that would be a multiplication. So, okay, and now, well, how would we approach that? So let's ask one question here. Let's see how it looks like. So in how many different ways, different distinguishable ways, right, we can rewrite letters in banana? Okay, so by using that formula, so we know we have 6 letters, right? So we have n factorial over n1. We only have 3 different letters, b, a, and n. So n1, n2, and 3. But it's equal to 6 over 3 factorial times 2 factorial times 1 factorial. Okay, because, you know, this word has, again, 6 letters. 3 of them are A's, 2 of them are on, and 1 of them is B. So that's why 3, 2, 1. So that's going to be equal to, so 6 times 5 times 4 times 3 factorial over 3 factorial times 2 factorial and 1 just 1. So 3 and 3 cancel out. 2 factorial is just 2. We're going to have 6 times 5 times 2, which is equal to 60. Right? And well, if you don't believe me that it's 60, we can write out all of the possibilities. Right? All of the possibilities. And here we are. Right? And there's precisely 60. Right? 60 different outcomes, distinguishable ways that we can write letters in banana. Okay. So now let's go ahead and talk about combinations. So when you count the numbers of possible permutations, right, order is important. So as a final topic, essentially, we will be looking at selecting those subsets of a larger set in which order is not important, right? So we can have order in our case is not important, right? We're not just strict on that. We can start at the same letters, we can end with the same letters. So essentially, let's go ahead and take a look at the formula. It's almost the same as permutations, but with a slight tweak to it. So combinations are as following: number of combinations of n elements taking r times combination. Like this. It's going to be very similar to permutations, but divided by r factorial. Okay, so an example of that. So in how many ways can 3 letters be chosen from this letter list? Okay, so we have A, B, C, D, and E. Order doesn't matter. Okay, so essentially, we're looking for 3 different ways. We have 5 letters, right? So C of 5, we have the 3 ways, so that's equal to 5 factorial over 5 minus 3 factorial times factorial. So that's equal to 5 factorial over 2 factorial times 3 factorial. So that's equal to 5 times 4 times 3 factorial over 2 factorial times 3 factorial. So again, 3 factorial and 3 factorial cancel out. 2 factorial is just 2. So we have 5 times 2, which is equal to 10. So there's 10 different ways we can do that. And is that true? Is that so? So let's write down all of the possibilities that we can have. And yes, indeed, we will get 10 different, essentially 10 combinations here. Okay, perfect. So as an example, a classic example of accounting cards, right? Accounting cards topic. So a standard poker consists of 5 cards dealt from a deck of 52 cards. And so let me set up here. So, and I'll attach a picture of it. So how many different poker hands are possible? Order of them is not important. So essentially, this is the figure we're referencing. So, okay. So here is a 52 deck. Okay. So what are we doing? We're choosing 5 cards dealt from a deck of 52. So that means the combination of a 52 using 5 is equal to 52 factorial over 52 minus 5 factorial times 5 factorial. Okay. And that's equal to 52 factorial over 47 factorial times 5 factorial. And that's equal to, so we're going to have 52 times 51 times 50 times 49 times 48 times 47 factorial, all over 47 factorial times 5 factorial. Right? So 47 cancel out. 5 factorial is going to be 120. And so that is equal to 2,598,906. Right? So there's plenty of ways you can draw a standard poker hand of 5 cards. All right. Perfect. Perfect. So, and the last problem for today is going to be, well, let's think about forming a swim team. So, you are forming a 12-member high school swim team from 10 juniors and 15 seniors. The team must consist of 5 juniors and 7 seniors. How many different 12 members teams are possible? Right, so what we're doing, we're choosing 5 juniors, so 10C5 times, we have 7 seniors out of 15, so 15C7. So we have to multiply them together. So it's going to be 10 factorial over 5 factorial times 5 factorial times 15 factorial over 8 factorial times 7 factorial. And that's equal to, so if you simplify and use a calculator here, you're going to get 252 times 6,455, which is equal to 1,621,620 different ways and combinations. All right. Thank you, students. And definitely go check out my other videos and subscribe. Thank you, and see you in the next video.